Hi, thank you very much for doing this interview. Before we start, I would like to ask you to briefly introduce yourself and say a couple of words at work, your education and your research interest.
Hi, my name is Daattavya Aggarwal. I'm a mathematical physicist. I'm originally from India, where I did my undergraduate degree in engineering physics, and then I moved to Oxford to do a master's in mathematical and theoretical physics. And I'm mostly interested in using tools like quantum computing and machine learning to help solve problems in areas of mathematical physics like geometry or string theory, and other interesting problems in theoretical high-energy physics. Thank you very much for having me.
Thank you. Which quantum-related project are you most proud of and why?
I've done a number of quantum related projects in my undergraduate years. I would say the one that I'm most proud of is this project I worked on where we found relations between quantum circuits and Boolean polynomials. This was essentially an extension of previous work done by Ashley Montanaro, where we found a way to represent any quantum circuit as an equivalent Boolean polynomial. And I would say I was most proud of this work because it was the first time that I actually managed to get published. I was able to present my work at a conference, and also it was quite interesting where it felt like a very sort of approachable task, which, in the sense that it was just beyond the bounds of sort of my knowledge, and you can use a bit of creativity to get a new idea. Whereas in some of my other kind of projects, it felt like the learning curve was extremely large, and I was mostly just trying to learn new things, but not really being creative. Whereas in this project, it was, you really had to just come up with a very small thing. It's a very, very small kind of push forward, but it's still something that you kind of, it's the kind of thing that I was interested to do when I thought that I wanted to do research. It felt a lot more like real research as compared to just reading a lot of papers and trying to understand the field.
Right. And how would you compare adiabatic quantum computation, gate-based quantum computation, and which one do you like better?
So I would say that I think both adiabatic quantum computation and gate-based quantum computation have their own use cases. So far, I would say that I think adiabatic quantum computation is preferable for a number of problems only because we have a lot more hardware where we can actually realize these the problems that we're trying to study. So I was quite fortunate. I worked on a project related to developing these benchmarking tools for icing machines, which are essentially the physics on which a lot of adiabatic quantum computation systems are built. And companies like D-Wave and Rigetti have been sort of leading this field where they've developed quantum computers whose topology limit the kind of computation that you can do, but they're good at simulating Hamiltonians, and you can find their ground state. So I think, but the benefits of a gate-based approach is it's a bit more universal. You can model a larger variety of problems. Not all problems are sort of amenable to be an optimization problem, but I think both of these fields kind of need to sort of develop hand in hand. And also, when it comes to sort of incorporating machine learning and things, there's a lot of interesting work at the moment where people are using a genetic algorithm, which is quite a standard technique in deep learning. And you can actually do genetic algorithms on adiabatic quantum computers. This was something quite new, which I learned about, and it kind of linked back to some work I did a few years ago, and I thought this is, quite interesting, and you can see how you can incorporate these tools together. So yeah, I don't have sort of a concrete answer which one I think is better. I think they have their own use cases. But I would definitely say I think the implementation in hardware for adiabatic quantum computers is probably a bit better than a generalized quantum computer that can just simulate any circuit.
Right. How would you explain string theory to a complete layman?
Yeah, so this is something that I've been trying to do because over the past sort of few months, I've had a lot of conversations with people from computer science who know a lot more about machine learning than me, but I know a bit more about string theory, and it's finding a common ground is often challenging. I would just say, so string theory is essentially this kind of, well, it's not so novel anymore. It was developed in the 70s. It was initially a theory for nuclear physics. And this was before we found out about quantum chromodynamics, which is a better theory. But the idea of string theory is that the fundamental sort of particles that make up our universe are these one-dimensional loops and vibrating membranes, although that was discovered a bit further on. And the only reason to call it string theory is essentially if you look at sort of the basic equations of how you can get electrons, protons, quarks, different particles, subatomic particles that make up the world, the equations look like the same equations that you would get for a classical string. So string theory, calling it string theory is really just sort of an interesting name to the equation. It's essentially just a wave equation. It's just the wave equation resembles that of how you would model a classical guitar string. Nowadays, people use string theory to talk about this theory of everything, but really string theory is sort of an exercise in mathematics. And the idea of string theory is to try to find a theory that can explain both quantum mechanics and general relativity, particularly in the cases where the theories are inconsistent with each other. And you can quite naturally find a resolution to this problem of quantizing gravity in string theory, because this hypothetical particle called the graviton comes out quite naturally as a consequence of some of the basic equations of string theory. The issue, of course, is string theory says that we live in 10 dimensions or 11 dimensions, 9 space plus 1 time, or 10 space plus 1 time, which most physicists and people working in string theory also agree is a bit crazy. There is no experimental evidence as of date for these extra dimensions, although there are ongoing experiments at CERN where they're trying to find these extra dimensions. So my current work is really actually focused on this. Our understanding of the standard model, which is sort of the name we give to the most developed theories, the most developed quantum field theories, is very, very strong. It's some of the most precise calculations that have been done by humankind. And the work in string and the standard model is a model that is a 3+1 model. So 3 space-time dimensions and 3 space dimensions, in 1 time dimension. And most of the work that I'm interested in at the moment is trying to reconcile how we can say that the actual real thing is a 9+1 space-time and bringing that back to the 3+1 that we live in. This constrains the kind of geometry of these extra dimensions. And yeah, this is where there's a lot of very, very interesting work at the moment on utilizing machine learning and quantum computing to help figure out which is the correct extra dimensional space so that our theories match. So that we can reproduce the standard model.
Right. Can you please tell me what is quantum scrambling and why is it useful?
So quantum scrambling is a concept that was developed to try to understand a quantum analog of classical chaos theory. So in classical chaos theory, if you consider something like a three-body system, you get very non-linear behavior, which essentially means that when you have two bodies, you can kind of perfectly model how they're going to behave at large time. But if you introduce a third body, even though you're starting with the same equations, it's very, very tough to model or predict how the system is going to behave. Quantum scrambling was an idea to try to find a quantum analog for classical chaos theory. And essentially, quantum scrambling talks about how much time does it take to start with a state that we have full information about before we reach a scrambled state where you cannot reproduce the local state. You cannot reproduce the initial state. So scrambling time is a measure of how long it takes. If you have an initial quantum system that is well defined, you introduce some very small local perturbation, you perform some operation on it. Perhaps you're trying to do a measurement, perhaps you're trying to apply some operator to your system, and you reach a state where you have no idea of what was the initial state. So this is somewhat analogous to how in chaos theory, you can get, if you start with a three-body system and initially you fix your initial conditions, you don't look at it, and then at some time t is equal to t naught, the system is behaving in a way that you can't reproduce the initial conditions from. So scrambling is just a way to try and quantify that for a quantum system.
I see. One question from quantum computation. What is your favorite quantum algorithm and why?
I quite like the quantum version of the Fourier transform.
Okay.
And I would say it's, I think for a number of reasons. It's extremely widely applicable. A lot of the circuits that you're trying to use at some stage, utilizing the quantum Fourier transform is sort of the critical step. And I will admit I don't have an intuition of why it is so kind of ubiquitous. And also when I was learning about quantum computing, when I first tried to understand Shor's algorithm, it was quite it was very, very fascinating how this very well studied an applicable technique in sort of classical physics and mathematics, the Fourier transform, it's everywhere. It was just interesting to see how quantizing it is really the critical step for a lot of these algorithms.
Okay, perfect. How big of a problem is quantum decoherence, and what do you think, how it can be solved?
I think quantum decoherence is a very, very big problem. So yeah, just for the benefit of anyone who's not sure what we mean by decoherence, it's essentially when a quantum system is not behaving in a quantum way anymore, it's behaving classically. And a lot of experimental work and effort is trying to increase the decoherence time so our systems, so we can actually use our quantum systems in the way that they're imagined to work. I think that there is perhaps a general kind of misunderstanding and actually how big and hard of a challenge it is to increase decoherence times or build large-scale quantum systems that will behave in a quantum manner. I'm not an experimentalist. I have some friends who are working on this problem. There's a variety of approaches. People use different kind of Rydberg atoms or superconducting approaches, or there's approaches with ion traps and things. I don't think that it's just a matter of throwing sort of more money and kind of resources into it. I feel that perhaps the breakthrough for this will be through some sort of novel experimental setup. I can't really justify that claim beyond the fact that it's sort of decoherence is kind of inbuilt into the way that quantum mechanics works. And this might go a bit too far into the foundations of quantum mechanics and such, but ways to sort of decoherence can also just be thought of as a consequence of the measurement postulate in some way. And I feel like that's a bit more of a fundamental problem because most of the physics community doesn't know how that problem is actually resolved. I mean, people have different interpretations and they have their own favorite versions of quantum mechanics. And I feel that there's most likely going to be some link between what we think is probably the best interpretation of quantum mechanics and in how we can sort of solve this problem of decoherence to get to sort of reasonable quantum computers.
So do you agree with Einstein's definition of quantum entanglement as a spooky distance, spooky action at a distance? And how do you see quantum entanglement?
I will agree that it's spooky because I don't sort of quite understand it at an intuitive level. I mean, I don't understand most quantum mechanics at an intuitive level. My favorite interpretation is sort of the Everett interpretation. I think the many worlds seems the most kind of consistent to me. But quantum entanglement, I think, it is a hard concept to wrap your head around. But just because there isn't really a classical analog, I disagree in the fact that I don't really think of it as action at a distance, because action at a distance is sort of implying information traveling faster than the speed of light and those sort of things. But quantum entanglement is really a property of the system, and you need to consider the entire system as a whole. When we're talking about having a 2-electron system that reaches an entangled state, and you take 1 electron light years away, and you perform a spin, and you talk about how the spin of the electron at Earth changes instantly. That's kind of one of the things that I think Einstein was worried about. But essentially, I feel like the conclusion, sort of the resolution to this almost paradoxical idea, considering that classically that doesn't make sense since nothing can travel faster than the speed of light, is you can't consider both of the electrons when you separate them as 2 separate systems. They're part of the same system. So yes, I will say I don't have sort of an intuitive understanding of it. It does feel a bit hard to wrap my head around, but I don't think calling it action at a distance is quite right. Of course, I mean, when Einstein was doing this, none of this theory that I have the benefit of knowing had developed at any point. And I feel that if Einstein was sort of alive today and he kind of read through, he might disagree. He might actually, solve a lot of the problems that we're struggling with. But perhaps he would rephrase what he meant by action at a distance for quantum entanglement.
Right. And now a question about different areas on physics, mathematical versus theoretical physics. What are the main differences and similarities between these two fields?
So first of all, I'll talk about the differences.
Yeah.
I think the major difference really is what the end goal is, what the objective of the fields are. Theoretical physicists are essentially interested in sort of problems that are directly related to the real world, even if their sort of methods might seem very abstract and devoid of practical use. The ultimate goal is to reproduce the measurements and things that we see in the real world. Whereas when it comes to mathematicians or even people who are doing mathematical physics, a lot of the problems that they're working on are self-contained. So as a very, very simple example, when I was talking about string theory having 10 or 11 dimensions, the way that we reconcile 10-dimensional string theory is with this concept of something called the Calabi-Yau manifold. And people showed in the 80s, almost simultaneously, the physicists and mathematicians actually reached this conclusion at the same time, which was a very interesting story in itself, that the correct sort of geometrical space to reproduce the physics that we knew at that time is the Calabi-Yau manifold, which has quite severe constraints. Now, still an open problem in mathematics is how many Calabi-Yau manifolds are there that are in 6 real dimensions? We're interested in 6 real dimensions or 3 complex dimensions, because if we have 10-dimensional string theory, we want 4 plus 6. And very interestingly, we know that there's only one Calabi-Yau manifold in 1 complex dimension. There's a fixed number in 2 dimensions. There's a fixed number in 4 dimensions. In 3 dimensions, we have no idea. Whether or not there's a finite number is also an open question. So the number of Calabi-Yau manifolds in 3 complex dimensions could even be infinite. So this is a very interesting mathematical problem in of itself, and mathematicians are interested in that. However, a theoretical physicist is only interested in the fact that, well, if string theory is correct, if we know that some of these Calabi-Yau manifolds in 3 dimensions are what we need, we don't care whether or not they're infinite or not. If we can find the right one, that's it, and where we can progress with the field. The similarities, I would say, is perhaps how the approach of people working in the fields are in terms of how they achieve these goals, in the sense that there is kind of the search for simplicity, a search for equations or fundamental laws that explain multiple things, rather than trying to sort of justify each individual measurement, or developing sort of techniques that are, I guess, applicable to a wider variety. The approach, I feel, for both of these fields is generally quite sort of focused. But yeah, I would say that is essentially the major difference. But of course, most of the things that they're studying are kind of interchangeable. And a lot of the people who are working in this kind of field converse with people on both sides. Rydberg, my experience with Rydberg physics is essentially this concept of a Rydberg atom, which was something that I worked on as an undergraduate when I was doing my first project related to quantum computing. Rydberg atoms are sort of one of the experimental approaches to develop a quantum computer, because they allow us to get these sort of well-defined different states. So when we talk about a qubit in quantum computing, which is the analog of the classical bit, we need a ground state, which we usually write as a 0 ket, and we need an excited state, which is usually a 1 ket. And Rydberg atoms are a good proxy for this, because you can, with a Rydberg atom, it refers to this atom where you can have these very well-defined ground and excited states, and it's quite easy to know whether or not your system is in the excited state or ground state. So yeah, I think that's why it's one of the sort of approaches. There's a variety of ways to sort of simulate a Rydberg atom. You can use different kinds of elements. I think cesium is generally one that was quite preferred by people, at least when I was working on these projects. And it was sort of accessible in the sense that, even at my undergraduate university, if there's a atomic physics laboratory, you can create Rydberg atoms in most kind of university environments. So it's I believe it's sort of less less expensive, less resource heavy as compared to making a 20 qubit quantum computer like IBM has. It's a bit more approachable to sort of start doing some simple experiments.
Can you talk about your master thesis here at Oxford? What was it about?
Yeah, so in my master's thesis, I worked on Calabi-Yau manifolds and mirror symmetry. It was essentially more of a reading project in the sense that it was meant to be equivalent to a 16-hour lecture course. So I didn't do any novel research, but essentially I learned complex geometry, complex manifolds, and the main focus of the thesis was about Yau's proof of Calabi conjecture. So Calabi-Yau is named after two mathematicians, Eugene Calabi, an Italian mathematician, and then Xingtao Yau, a Chinese mathematician, who Calabi conjectured that something like a Calabi-Yau manifold should exist, and Yau proved this. And in my thesis, I sort of developed the background theory to that, gave a proof for Yau's theorem, and did some calculations on different types of Calabi-Yau manifolds, finding topological numbers, that Hodge numbers, Fedde numbers, etc. And I concluded with sort of talking a little bit about mirror symmetry, which was this proposed symmetry from the physics side, which is quite important in string theory, and seeing how Calabi-Yau manifolds do exhibit this mirror symmetry.
You work as a data scientist. Can you please tell me which background do you think is the best for a data scientist? Mathematics, physics, computer science, engineering?
Yeah, well, this is a sort of a question that I'm interested in myself because my background, I haven't worked with data science in the past, but seeing how sort of important it is for this emerging field and seeing all of the new results, and I found this field very interesting. I've been getting into learning data science. I think that mostly any sort of STEM background is probably good to get into data science. It's I would say the most important sort of skill set is just knowing how to sort of interpret data, having a basic kind of understanding of statistics and probability, more than whether or not you've done mathematics or physics or computer science or engineering. I think everyone can, at least I hope, sort of develop their skills in data science.
Can you please tell me something about your job? What are you working on as a data scientist?
Yeah, I'm working in this new startup called New Health, which is essentially a startup focused on trying to monitor neurological conditions like Parkinson's disease, and eventually we want to move on to Alzheimer's and dementia. So it's a health tech startup. We're still very, very early stage. My role, I worked with OPDC, which is Oxford Parkinson Disease Center, which is based in the neuroscience department here, as a data scientist for the past 3 to 4 months. Essentially, it gave me a chance to get some practical experience in applying simple data science techniques, doing sort of the background sort of work, which is very, very important in being able to do any data science application, such as cleaning up your data, knowing how to deal with missing data, sort of crucial elements that I didn't have any experience with. And now the idea is to try to translate that research into a product that we can hopefully give to patients and clinicians. So I don't understand the neuroscience very well. I've been picking up some things as I've been working on the job, but really my role is to try to translate this research into this new product.
The greatest quantum physicist of all time for you?
Oh, the greatest quantum physicist of all time. Yeah, I think that's quite hard. I think I would say Paul Dirac. At least so from sort of my experience and my studies so far. Just this idea of sort of negative energy, or it's very, very hard to sort of put yourself in their shoes and try to see how he came up with this and how ubiquitous it is now, and how so much of our modern theories are kind of built upon it. I mean, it's also very, very hard to not say Schrödinger, since, especially considering if I'm, many worlds is sort of my preferred interpretation, and that's just all about how Schrödinger's equation is essentially all the world really is. And all these stories about how he didn't quite believe it, and it's such a simple and beautiful equation. So I would say it's a hard kind of choice between the both of them, but there are just so many people who you could name there. But I think I think really what sort of excites someone is trying to put yourself in their kind of shoes, and how much of a leap were they able to make from the information that they knew. I would say that both of them did a lot of work for quantum physics, especially, along with a host of others.
Right. And what do you think about Richard Feynman and his legacy?
Yeah, I mean, I think Feynman is well, an extremely well accomplished physicist that was sort of developing quantum electrodynamics, doing so much work with renormalization, figuring out so many issues. More than that, I also think that Feynman's legacy is also just the impact he's had on the general public, and sort of giving a kind of a face to science in a way where popularizing it, in the sense some of his popular books are extremely common. I've read a few of his books. It's extremely sort of heartening to be able to read directly from someone who was at the frontier of their field. And yeah, I mean, we're talking about quantum computing today, and Feynman, of course, was the person who initially sort of thought of the idea of a quantum computer in the 80s, thinking that we should, if you want to do simulations of these chemical experiments, it should really be on a quantum computer. So there's I think in my mind, though, Feynman's sort of legacy is being someone who really bridged this gap of popular science and very, very hardcore kind of new progress in a very good way. And I think that's quite a hard thing to do. I feel like in the modern day, there are maybe few people who can really balance both of those, being able to talk well about their work and represent science in a good way, but then also having enough sort of time and energy to be able to push research forward.
How do you like living and working here in Oxford?
I think Oxford's great. I was initially only going to be here for sort of my master's course, which was 9 months in total. So I thought I was going to be in Oxford for about a year, but I've been here now for about 2.5 years. I think Oxford's a very nice city to be able to live in as a young person. I feel very privileged to be here. There's a lot of very smart, kind people. I think also importantly, I feel like Oxford's a very sort of welcoming environment, where there's a very healthy work-life balance when you're working on sort of these kind of things, and everyone is sort of under the pressures of academia. I feel like it's quite easy for the environment to become extremely competitive and toxic, and I think Oxford is particularly very, very good at having a very positive work-life balance. And as a city, yeah, I think it's very beautiful. I mean, I think Oxford is extremely well accomplished. So my course was entirely in COVID, so most of my teaching was done online. So it's hard for me to really comment on how the teaching resources were. I think one thing that Oxford did do all right in was translating the academics, but I do think that they could have sort of done a bit better in translating sort of the social life and getting interaction between students during the COVID year. So I think particularly for sort of maths and physics, it's quite important to have communication with your peers, maybe when you're talking on problem sets or dealing with difficult concepts. And that was a hard thing to emulate during COVID. But I think the university tried to do all it could when it came to sort of translating the academics. And in terms of research, I mean, Oxford is sort of a leading university in most of these fields that I'm talking about. The field that I'm very, very interested in at the moment of using sort of machine learning, particularly for these problems in string theory, a lot of the people across the world who are working in different groups originated at Oxford, either as a student or a postdoc or did their PhD here. So Oxford definitely has very far-reaching influences. And yeah, it's a privilege to be able to live and study here. We haven't talked about AI. So what do you think about artificial intelligence? I think artificial intelligence is an extremely powerful tool. when it comes to problems in math and physics, I do feel it's almost kind of a shame how we haven't really been using AI so far. So particularly when you talk about this problem of Calabi-Yau manifolds, we've had data sets of Calabi-Yau manifolds. There's a very famous Korsakoff data set, which actually came from Vienna. This was developed in the 90s, and it's about 500 million examples of Calabi-Yau manifolds. We've had this for 30, 35 years, but really using AI or the most kind of advanced data science techniques has really only been done over the past 4 or 5 years. And it was a bit, when I first was getting introduced to this field over the past year, I found it a bit difficult to kind of understand why, nobody had tried it yet. I feel like there's perhaps a bit of hesitancy in using interdisciplinary techniques in some circles in academia. And in that sense, I think AI is really a very powerful tool, which is useful to most communities. When you talk about sort of pure mathematics, there was this landmark paper in 2021 that was published in Nature where researchers from DeepMind collaborated with professors from the University of Oxford and a professor from the University of Sydney to prove some fundamental results in knot theory and graph theory. And that was something that kind of interested me quite a lot. I'm not quite sure right now, to be honest, about what really is the relation between AI and mathematics. This is very much an ongoing kind of field, and then there's, of course, a whole different project where people are trying to formalize mathematics through computer softwares, things like Lean and things, where the idea is that if you can formalize all of mathematics, you can maybe use AI to develop new conjectures or theorems. The community is very, very split. There's people on both sides with very good points, and I don't really have a strong opinion on that side of things. But yeah, I feel like AI is kind of an indispensable sort of tool where it feels like if you're not thinking about whether or not it would be a good thing to use, you are making some kind of a mistake, in my opinion. I don't think AI is the right thing to do for every problem. In fact, I think there's a lot of problems where maybe just using classical computation techniques might be better. But this approach of keeping, this powerful AI tool in mind, I think will help progress a lot of these fields a lot quicker.
Okay, so before we finish this conversation, do you have anything to add for our viewers?
Yeah, I would say, I avoided trying to learn about data science and coding for the longest time because I was very, very sort of interested in just doing my project related to math and physics, and I would pick up whatever little, pieces of initially just, coding and then data science techniques when I needed to do a particular project. But I feel like it's something that's sort of, it has such sort of wide-reaching applications that if you're interested in anything STEM related, I feel like learning about a basic course on statistics and probability or doing a bit of data science work is probably extremely beneficial. It's something I wish that I did much, much earlier that I'm trying to sort of do now. And yeah, I guess that would be like my specific kind of advice.
Thank you so much. It was a real pleasure talking to you, and hopefully this is the first of many times you and I are going to talk.
Thank you. Yeah, thank you very much for having me. I enjoyed the conversation quite a lot, and I think this is a very, very great idea, and I wish you a lot of success with your podcast.
Thanks so much.